Welcome to the Walton Pi. Today we are going to be talking about U-substitution. So sometimes we are given an integral that looks close to something we know how to integrate, but it isn't quite there. U-substitution is often used to turn an integral into something that we do actually know how to integrate, and then we are able to then back substitute to be able to solve for what the actual integral was. So for example, we might be given something like 2x plus 7 times x squared plus 7x plus 8 to the 13th. This is pretty close to like something to the 13th, but it's just a bit more complicated than that. The way that we would try and rewrite this is we can make a U-substitution to try and rewrite the integral into something we know how to integrate. So for example, we could expand this out and then we could integrate. But expanding out x squared plus 7x plus 8 to the 13th and then multiplying it by 2x plus 7, that is going to be an absolute nightmare. It's doable, but you really don't want to do it if you can avoid it. So instead, we could try to replace the part that's the most complicated with a new variable u and see if that simplified the integral at all. So in this case, the thing that's the most complicated is the fact that we have x squared plus 7x plus 8 raised to the 13th. So we might want to say u equals x squared plus 7x plus 8. So then we would just have a u to the 13th, and then we would hope that the 2x plus 7 would disappear with part of our du. So what we would be able to say is we can say that u equals x squared plus 7x plus 8, then the derivative of u, or du, is going to be a 2x plus 7 dx, or the derivative of what u is equal to. Since then that's what we had left over, we had a 2x plus 7 times a dx. After we replace the x squared plus 7x plus 8 with u, we have a valid u substitution. So if we make our substitution, u equals x squared plus 7x plus 8, and du is 7 dx, then this turns into the integral of u to the 13th du, which is something that we can do. That follows the power rule. So that means that is equal to u to the 14th over 14 plus c. So this is equal to x squared plus 7x plus 8 to the 14th divided by 14 plus c. That's how we can use U-substitution to be able to simplify our problems. So if u equals g of x is a differentiable function on an interval and f is continuous on the interval, U-substitution is basically inverse chain rule. It's how to undo a chain rule problem. So if we have the integral of f of g of x times g prime of x, that is the integral of f of u du. And then we are able to integrate that. And if our bounds go from a to b, we have to change our bounds when we are doing these problems. That is something that's very important to remember. Your bounds change when you do a U-substitution. You can't just keep the same bounds because that's going to give you the wrong answer. Your bounds will change when you do a U-substitution. So for example, if we were integrating, if we were to look at the integral from 1 to the square root of 13 of 2x times the square root of 3 plus x squared dx. If we make our substitution where u equals 3 plus x squared, because that's the piece that's the most complicated, we have a function under a square root, then our du is 2x dx. So this turns into the integral of the square root of u du. Now our important change is that our bounds are now what our u function is at our x values. So when x was 1, u is going to be plus 1 squared. And when x is the square root of 13, u is 3 plus the square root of 13 squared. So that means this turns into the integral from 4 to 16 of the square root of u du, which is u to the 3 halves over 3 halves evaluated from 4 to 16, which is 2/3 times the square root of 16 cubed minus the square root of 4 cubed, which is 2/3 times 64 minus 8, 2/3 times 56, or 112 thirds. That is how we would do U-substitution in this particular problem. Other times we might not see the substitution the way it is written directly. For example, the integral of tangent of x. That's not a form where we have an easy U-substitution. However, if we were to first rewrite it as sine of x over cosine of x dx, then we might start to think, oh, the derivative of sine is cosine, so maybe I'll let u equal sine of x, then du is going to be cosine of x dx. So I make the substitution, I get u over cosine of x times dx. We are kind of running into a problem. We need the cosine of x times the dx, not dx divided by cosine of x. So that tells us that our substitution u equals sine of x might not be the right substitution. So instead, if we were to substitute u equals cosine of x, du is negative sine of x dx. So negative du is what we have, the sine of x dx. So we can replace that with a negative du over u, which is the negative natural log of the absolute value of u plus c. So then we can replace u with cosine of x. So the integral of tangent of x is negative natural log of the absolute value of cosine of x plus c. That's how we might be able to use U-substitution in this situation. Now, we might also be able to replace the negative natural log. We can move that negative in as an exponent, so it becomes the natural log of 1 over cosine, which is the same thing as secant. So the integral of tangent of x dx is natural log of the secant of x plus c. I hope this video was helpful in understanding U-substitutions. Just remember, take the complicated piece, make it U, and hope that works. If it doesn't, try something else. But I hope this video was helpful. Please check out some of my other videos, and please like and subscribe if you haven't already, so that I can continue to make these videos. Have a good rest of your day, and good luck with the rest of your math.